This is section 1.6, inverse functions, starting with the definition. So the inverse of a function f is denoted, or we can say written by, f to the negative 1. So this would be f, this would be f inverse. So we don't want to say f to the negative 1, we read it as f inverse. And is a function in which the inputs or x values switch with the outputs. So we're taking x and we are literally switching it with y. So if you look at this example, if this is my x row and this is my y row, for an inverse of that, this becomes my x values that were before my y, and these become my y values that were before my x. So we're literally taking the x's, making them y's, and vice versa. For an equation, this is what an inverse of an equation would look like. So this is f of x, x plus 1. F inverse of x would be x minus 1. So there is a mathematical way to do this. It's not just taking anything that's positive and making it negative, as you can see. And I'm going to show you a couple examples of how to do that. So here, to verify that two functions are inverses, there's two ways to do it. You can either do it algebraically, or you could do it graphically. So algebraically, we have to know how to find the composition of a function. So that means plugging in one function for another. And algebraically, if we plug in f inverse of f, we should get out just x. It should equal x every time. And the same vice versa. So if we take f inverse and plug in the f function, we should also get x. So it's not that these two things are going to be the same. We literally have to get that value x in order to show that they are inverses. So here we have an example. Show that f of x equals negative 7 over 2x minus 3, and g of x equals negative 2x minus 6 over 7 are inverses of each other. So we are going to do that. So here I have the two functions written out. And in order to show that these two are functions, we need to show that f of g of x equals x. So first, we are going to solve for f of g of x. That's plugging in the g function anywhere we see an x in the f function. So that would look like this. So now when I plug this in, we can multiply across the top and bottom. Since we're using multiplication, if we want to make our lives easier, we have a 7 on top, 7 on bottom, so we can cancel that out. So on top, we'll multiply this whole top piece by negative 1. So we get positive 2x plus 6. And on bottom, we multiply by 2 times 1, which is 2. We have the minus 3. So now on top here, we can factor out a 2. Get 2x plus 3 over 2. These 2's cancel. So we're left with x plus 3 minus 3. So x plus 3 minus 3 gives us x. So check, f of g of x equals x. But now we're not done. We want to do the opposite way and show that g of f of x also equals x. All right, so to show g of f of x equals x, we're going to take the g function, and for this x, we're going to plug in the f function. So negative 2 times 7 over 2x minus 3 minus 6 all over 7. So here, where we saw an x up here is where I plugged in the entire f function, plugging in f into the g function, and now we're going to multiply. So when we distribute the negative 2 over here, we get negative 14 over 2, which becomes negative 7x. And then negative 2 times negative 3 is positive 6. And we have also a minus 6 on top over x. So minus 6 plus 6, that cancels out to 0. So we're left with negative 7x over 7. And actually, this should be a negative. So this should actually be a positive 7. right? Fix that. And then 7 over 7 cancels out. So we are just left with x. So since g of f of x equaled x, and we already showed that f of g of x equaled x, this means that f and g are inverses of each other. So we looked at the algebraic method for showing that two things are inverses. Now let's talk about graphically what you can look for. So if two functions are inverses, they will reflect over the y equals x line. So you can see here we have f of x is this blue line, f inverse of x is this purple line, and this is the line for y equals x. So you can see they're a mirror image on either side. So graph the functions on a graphing utility, and you have to determine if they are symmetric across y equals x. So if you were to graph these two things, you can do it on Desmos. You will see that across this line, they do reflect, and they are in fact inverses. So finding an inverse. To find an inverse of a function, we first want to replace f of x with y, if necessary. So if we have an equation that already has y equals, we don't have to do that step. Our second step is switch x and y in the equation. So we are literally taking x and switching it with y, because that's what an inverse of a function is. And then our last step is to solve for y. So we want to get it as a y equals equation. And then if necessary, we can change it back to f inverse of x. To show that it is the inverse. So a couple examples. So if we want to find the inverse of the following functions, our first function here is y equals 4x, so we can skip that first step. It's already in y equals form. And now we're literally going to switch x and y. So you can see where there was a y, I wrote an x. Where there was an x, I wrote a y. And now we solve for y. So we get y equals x over 4, and that's our inverse. If it doesn't start with f of x, you don't have to change it to f inverse of x equals x over 4, but you can if you want to. For b, we have f of x, so we are going to switch that to y. And now our second step, switch x and y. And then our third step, solve for y. So subtract 1 from both sides and divide by 2. And make sure you divide the entire thing by 2. X minus 1 all over 2. In this case, since we started with an f of x, we do want our final step to switch this to have f inverse of x equals x minus 1 over 2. And our last example, once again, we start with y, so we switch x and y. And then we're going to solve for y. Add 1 to both sides. We get x plus 1 equals 2y to the third. We're going to divide by 2, divide everything by 2. X plus 1 over 2 equals y to the third. And now we are going to take the cube root of both sides, and this cube root should cover the entire fraction. So our inverse is the cube root of x plus 1 over 2. The last thing is telling if an inverse exists for a function. So we already know how to tell if something is a function. We use the vertical line test. We draw a vertical line and see if our function crosses it more than once. To determine whether or not a function has an inverse, we need to tell if the function is one-to-one. So what one-to-one means is not only does every input have one output or every x have one y, but also every y has only one x. So we consider this a one-to-one. It would pass what we call the horizontal line test. So if you were to guess, that is correct. We want to draw a horizontal line and make sure that the function does not cross more than once. So looking at this first function, this one is a little bit tricky. So a function, it looks like it's approaching the x-axis. It's actually getting closer and closer and closer. It's never actually going to touch that x-axis, but it gets infinitely closer. So if we were to draw a line this way, you might be saying, well, it looks like it's going to touch it here, but it's really going to be like 0.00001 off from that. So this would pass both the vertical and the horizontal line test. So if we drew a line this way, it only crosses once. If we draw along this way, it only crosses once. So this would have a function. It is one-to-one. So yes. Same thing with this. If we draw a vertical line, it only crosses once. If we draw a horizontal line, it only crosses once. So this is also one-to-one. This function does have an inverse. Here, this passes a vertical line test, but does not pass the horizontal line test. So if I draw a horizontal line, you can see 1, 2 crosses twice. So this function does not have an inverse. So fun fact, not all functions have inverses, and that's how you tell if it does or not.